So this is a design problem. We're not looking at the word problem itself. And we never start these asynchronous sequential networks with a state diagram. We modify it too many times down here. You really can't get a sense of all the issues unless you start at a state table. Now, this is the bare bones information coming from the word problem, skipping the state diagram. And what we need to do is complete this. So A is always going to slip down to B here because B is unstable. A is always, if it moves to here, it's going to slip down to C. So there's no way it's ever going to reach this state. So all of these are unstable or they're don't cares. Now B wants to return to A. B is never going to get to this state because it's going to slip up here to A or it's going to slip down here to D. So all of these are don't cares. C can never get here because that'd be a 2-bit change. But it's going to slip up to A or it's going to slip down to E. So this is a don't care. So you get these don't cares on a diagonal like this. D, if it gets to here, is going to slip down to F. Same thing with E. It's never going to get to here or to here if we slip. So let's slip up to B. Okay, that keeps this don't care alive. We don't want to go to here with F. If we go right, because we want to slip here. So let's slip up to A. That gets us back to starting point. And here we would slip up to E. Right? E has the same output of 1. Okay. Well, really, we want this to be a 1. Well, we'll go through and fill in these don't cares later. Okay, so let's build an implicant table. B, C, D. All right, now we're going to compare A to B. And they most definitely could equal each other. We're going to compare A to C. And they could most definitely equal each other. We're going to compare A to D. C would have to equal F. That's the only requirement. E. A and E. A and E. C would have to equal F. A and F. C would have to equal F. All right, now let's just check C and F real quick. Can C equal F? Yes, yes. C would have to equal F. That's redundant. E would have to equal... No, they can't. So C cannot equal F. B and C. Yes, yes, yes. D would have to equal E. All right. B and D. Yes, 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 yes. B definitely equals D. B and E. Yes, yes, yes. D would have to equal E. We already know. No, we don't know anything yet. D would have to equal E. D would have to equal E. Okay, let's check D and E. D and E, no. Their outputs don't match. So this isn't going to match and this isn't going to match. B and E. Yes, yes, yes. D and E, no. D and E is not going to match. B and F. Yes, yes, yes. D and E, no, it's not going to match. C and E. Yes, yes. C would have to equal F. We already know that's impossible. D and F. Yes, yes, yes. D and E. No, we know D and E is not working. E and F. Yes, 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 yes. Okay, so now we're going to do our coverage map. We have A and B right here. We have A equals C right here. We have B equals D right here. And we have E equals F right here. All right, we have A, B, C, D, E, and F. So this covers A and B. This covers A and C. This covers B and D. This covers E and F. So we're going to choose this one, which covers these two. We're going to choose this one, which covers these two. And then we're going to choose this one, which covers these two. And we're not going to use this one. All right. So let's rebuild the state table. We know that A and C. So this is going to have to be a B. C. This is going to have to be an E. A and C. This is going to have to be a 0. So we can get rid of C. B is going to have to equal D. So this is going to have to be an A. Yeah. It's going to have to be an F. Yeah, DD. It's going to have to be a 0. And this is going to have to be a 0. Okay, so now we can get rid of D. E and F. It's going to have to be an A. This is going to have to be a B. F, F, E, E. This is going to have to be a 1. So we can get rid of F. All right, so now F and E are the same. So we're going to put down E here instead of F. Put an E right here instead of F. And we don't have any D anymore. Any D's? No. D is what? B. So that's a B. Any more D's? All right, any more C's? C is also equal to A. So it's going to be an A. A, B, and E. A, B, and E. A, B, and E. We're done. Yeah, looks the same. They just use different symbols here. They collapsed A and C, B and D, and E and F. So the next step is to do the bounce test. So what is the bounce test? Well, we take every stable state and bounce it. I'm going to do the ideal path in green. So ideally, this is what happens. Ideally, this is what happens. And then we bounce. So we bounce here, which is going to race up to here. And then we apply our original input again, and we should land at the same state. So that one checks out. So we bounce back to this column, and then we change our input again, and we're going to go over to here, and we end up at the same place. Checking another pair. This is our ideal path. This is our ideal path. So we've moved from here, so we bounce back, slip up to here, and then change our input again, and we end up in the same state. So this one checked. All right, here we bounce back, and then we change our input back, and we end up at the same state. So this one checked. So far, no problems. Okay, so we're right here, and we can't change to this one, so we're going to go over to here. That means we're going to slip up to here. This one can change to here. So it's going to slip up to here and stay stable. All right, now we're doing the bounce. That's the ideal. Now we're doing the bounce. So we're going to bounce back to here. We're going to stay stable there, and then bounce back, and we end up the same state, so that one checks. Final one. We're here. We're going to bounce back. That's stable. Then we go over to here. Okay, we're done. We've checked all 6 of those stable states, and there were no problems. Why we're doing this will become apparent as we get through Design 2 and into the combination lock examples. What we're trying to do is prevent essential hazards. They're associated with timing problems. It's going to be easier to show you that when we get to a more complicated example. I wanted to show you the discipline right now of checking for the bounce. It's pretty easy to check. What's interesting is there might not be a solution. The solution depends upon the word problem. So without really having a word problem, we can't really even begin the discussion of fixing them. This is why they're called essential hazards. They're essential to the word problem itself. This is when we might have to add the evil delays after building the circuit to solve them. Pretty cool. So we're done with the step that we've been calling the implicant table. Now we're going to scroll down to look at the transition table. So here what we're doing is listing off the transitions. Alpha goes to beta, there and there. That gamma goes to beta. So this one went to alpha, this one went to beta. Beta goes to gamma, right? We've already got that. So everybody goes to everybody. I don't think this is going to be hard. We're going to have 2 flip-flops or virtual flip-flops. If we put alpha here and beta here, then we can put gamma here, and we're going to slip or race through here. So let's say alpha is 0, 0, and beta is 0, 1, and gamma is 1, 0. All right, let's see what they did. Looks like they did it a bit differently, but they still have to race. So let's build this transition table. All right, let's circle the stable states and check. This part's the same, but right in here and here we have some differences. It looks like they're dealing with output flicker here. They're saying, well, if we slip up and down inside this column at this input, then we just lock in at 0. Don't care. So if we have a 1 and a 0, we could flicker. Same thing's true with these two. Now I think they left this alone and this alone because it truly doesn't matter whether it's a 1 or a 0. And they're leaving room for some simplification of the output circuit. But we'll deal with that later. In this transition table, we deal with the bounce, and that could add states up here and change the flicker. We deal with the 1-bit change, 1-bit Y change, and that could add some states, and that could force us to revisit the output flicker. In the transition table, you're sort of going around in a circle between this flicker, 1-bit change, and bounce. You're just sort of going around in a circle until everything stabilizes in your design. Okay, so the next step is to check the races. So a race check looks like this. We start here and we assume x2 changes to a 1. That causes us to race down to here, which causes us to race to right here. So we do the same thing over here. Is that a 1-bit change? Yes, that's okay. Is that a 1-bit change? Yes, that's okay. So that's a check. Let's do this one. We start right here and we go to here. We race down to here. So we start right here and we go down to here. That's a 1-bit change and we're stable. Everything's good. Okay, so this going to here is never going to happen because that's a 2-bit change in the input. This going to here is a stable, so that's not interesting. The only slip is right here. So we go to here, and then that slips us to here, and then that slips us up to here. All right, so we're starting here, that's a 1-bit change. And up to here, that's another 1-bit change, so that's okay. Now let's look at this one. Could go to here and slip down to here, here and slipping down to here. That's a 1-bit change. Everything's good. All right, looking at the last row, this one going to here is never going to happen. This could go to here and then slip up to here, and that's a 1-bit change. That's good. This one to here is boring. Here to here is never going to happen, so the only one interesting is from here to here, and that's going to erase us to here, and that's a 1-bit change. So that's good. So there's no racing problems. Next is a flicker check. The only flicker is going to occur through these don't cares. So we're going to move from here to here and then slip down to here. Okay, so if we're going to go through here, then it doesn't matter whether that's a 1 or a 0. If it's a 0, right, or if it's a 1, it's just going to change a little bit earlier. All right, what about from here through here down to here? That's from here down to here. It's the same issue, so it doesn't matter whether this is a 0 or a 1. There's going to be no flicker. Let's see, from here, there's not a stable state to get to here. It could go down. Let's see, from here you can't get to there because that'd be a 2-bit change in the input. So that's really the only 2 possible paths that we need to check the flicker. So there's not going to be a flicker problem. Okay, we're done with the flicker check. Now what we want to do is move down to the excitation table. You can see we have Y1, Y2, and Z as our outputs that we're trying to compute. And we're drawing our implicants, and they all overlap. See, that's what you're looking for. They overlap. That's a good overlap. There's just one here, so it doesn't have to overlap. Finally, we build the circuit. The goal is to build it without delays, and then check to see if it works. So our final step is to test it. And that's what we're going to do next. Here's the circuit. You can see I have lowercase y1 wrapped around to big Y1. There's big Y1 hooked up to little y1. Here's the network built by the previous Karnaugh maps. We can expand it up a little bit so you can see the whole thing. That's this circuit, but we're looking at it here in main. So you can see the whole thing. Now, I've gone through the options under the Simulate tab, and I've dropped down the number of iterations until it produces an oscillation to 200. So that should make it harder for this circuit to pass the test. I've dropped it from ignore to error out on undefined inputs. That should make it harder to pass the test. And I've added random noise to the component delays, and that should make it harder to pass the tests. Let's turn off the simulation and single step it. So once again, we're going to go from here to here. So we should pass through this intermediary unstable state of 1, 0 and end up with 1, 1 right here. Okay, so here we go. I'm going to go change x2's value from 0 to a 1. Now I'm pressing Control I. There's the intermediary unstable state. Now it slips down to here and becomes stable. Yeah, and all the blue's gone. Testing can blow up on you. This one has 2 places you can go from here. 2 from here, that's 4. 6, 8, 10, 12. So those are 12 possibilities that we need to test. We've just tested one. Now we're going to test another one just going back. So it should look something like this. We're right here, and we're going to go back to this column. So then we're going to go down to this column, and then we're going to go back up to here. So we should go through 2 unstable states getting back here. Now I'm pressing Control I. Okay, so now we've moved to here. Now we've moved to here. And now we're stable up here. So I'll leave it up to you to test the other 10. Just play around.